Okay, hello. I'm glad to see a few of you could make it to the live stream. So it's always nice for me to know that someone's out there watching while I do this in real time. So welcome. If you're watching the video later, hopefully you're having a good week. Um, so yeah, we have a busy week of content this week. We're adding to our toolkit. We're adding the ability to make decisions in our code so that we can respond to different situations um, in our code. The lab is not going to feel much like different situations. The lab this week is a lot more just getting you accustomed to the syntax of decision making. But you'll see when I encourage you to go look at project 2 again today or this week, that you will need this decision making and it will make it possible for you to do some interesting things in your project. Okay, so I'm not going to waste too much time just talking at you. So let me first just show you some of the lab work from last week. So the lab requirement for last week was simply that you implement functions and pass the unit test, but some of you actually made programs out of it. So I thought I'd show a few of those off because I just think that's super, super cool. So this is a CSCI 20 week 7 demos. So anyway, let me just show a few of those before we do other stuff because I like to celebrate the hard work that you guys do. So this I just thought was a clever, super clever idea. You weren't required to have a func main. That wasn't a part of the lab, but this person did a very interesting thing, which is they used their func main to put a note in here about what the purpose of the code actually was. So that was a super clever idea. Also with a note to me and to anyone else who might run this program that the real goodies are in running the unit tests. So that was a very clever idea as an enhancement for this person's lab work was to add a func main with that stuff in it. So super cool idea. Let's see what this one was. Yeah, this person just put a funny note in their main. And again, it wasn't a requirement, but this kind of little touch, just like I was aware that I could do a main and I put something fun inside of it. I thought was just kind of fun to show you guys. And then let's see what this one did. Yeah, so this person did a full-on program, which wasn't even a requirement, but it is very good practice to do a full-on program. I also thought it was kind of cool that they went and found characters for representing pi as an example, which you can do in Go. You can also, by the way, put emojis in a Go program. Maybe I'll do an emoji or two today. So anyway, I'll just do basic inputs, but this is like a full-on just awesome program that this person wrote. Not because they had to, but probably because the practice is good. They are honing their display skills. They went and found this square root symbol as an example. The little squared. Anyway, wow, very cool. Yeah, and passed all the unit tests to boot. So wow, that was awesome. And why not show off when you can show off? I totally would. Yeah, and here's another person who wrote a full program, but also kind of themed it a little bit. I'll just put in some numbers. So isn't this fun? This person, by the way, I hope that you like the second and more particularly the third project, where you will really get to kind of stretch your wings. So another cool program, and these didn't even require func mains, but these people implemented them just because it's an awesome thing to do. So good on you guys. That is really, really neat that you did that. Yeah, that made it kind of fun for me to work through the labs that some people actually took the time to implement those extra touches. Just because why not use your powers of Golang programming if you can? So they did, and there will be a payoff to that. that extra practice is going to make future work that much easier because they've repeated these things by doing that work. So wow, that's super cool. All right, individual project 2. Let me open it, and I will make an effort to go read through it before we leave today. And maybe I will offer a hint or two to get it going. All right, so that comes later. Let's work on the module. So we're in week 8. We're almost halfway there. Technically speaking, by the way, for you guys, we have 16 weeks of Golang programming, and then your final 4th project is due the end of week 16. Week 17, which some teachers will do final exams, but what we will do instead is a sort of a mini C++ training session, a C++ boot camp, so that those of you who are going on to Programming Algorithms 2 will have had an introduction to basic C++ syntax, so that when you get to Programming Algorithms 2, which was likely to be in C++, it won't be new and unfamiliar to you. They're very similar, Go and C++. Go is a much nicer language to work in than C++, though. Okay, so what are we doing? We are adding new constructs that give us the ability to make decisions in our programs. So we will have if statements, if else statements, which gives us sort of branching decision making. If a certain situation exists, do one thing, otherwise do something else. We have if else statements, which give us the ability to do multiple possible branches of a decision outcome. And then also the switch statement, which is not one of my favorite things to use, but it's another construct that I will show you that you can use to make decisions in a Go program. So having the ability to make decisions and make your program take different actions in different situations it's necessary to make software. But it's also a new, very powerful tool to add to your toolkit. And then we will, in the lab, find applications for these constructs, I will call them. So the if statement is a construct. The switch statement is a construct. It's a thing you can set up in your Go code to make different things happen in different situations. We will be doing all of this stuff in the context of functions. So we are going to just use functions for the rest of our time, and you will, however much more programming you do in life, you will just use functions like as not for the rest of your programming work that you ever do. So we won't stop in this class. We will still do everything within functions. We'll just be adding more power to our functions. A whole bunch of different options for readings for learning these constructs. This week we are starting to do Boolean logic, and that is crafting statements that yield true or false results, and then we use true or false to choose which branches to go in our decision setups. But the fancy word is Boolean logic. Homework as always. Lab as always. Yeah, I'll come back to this because we have a unit test, and I do want to go through some of the lab because some of it might feel a little bit intimidating if I don't give you a tip. And then this week, one of the things that I want to achieve in this class is have you understand. I see a spacing issue. Hold on, let me fix it. Right here. Have you understand that learning a new programming language in most cases is relatively trivial. There are differences in the language rules, what we call the syntax of programming languages. C++, for example, uses a lot of semicolons, whereas Go uses very few. But for all intents and purposes, if you know the Go language, then C++ is easy to learn. C is easy to learn. Java is easy to learn. Python is easy to learn. PHP is easy to learn. And hundreds of other languages. We call these languages as a category C-like languages because they all share features of the older C programming language, which is still very popular. So anyway, I want you to come out of this class with the knowledge that knowing Go is a gateway to many other programming languages. So to have someone tell you you're going to use a different language in a different class is not a big deal. And also, I want you to understand that if someone tells you that they know 6 different programming languages, that's not a particularly impressive thing to know. So what? Most languages that most people use are very similar to each other. Okay. So anyway, that's what the discussion is about. And we'll come back to this topic in different ways to have you go compare the Go language to other languages and the way that they do the things. So this week, how do other languages support decision making? What does an if statement look like in the Python language as an example? And then finally, the reminders, which includes the project, which is due on October 23rd, which is just short now of 2 weeks away. So the time to start working on this thing is now, basically. Okay, and then homework lab and discussion as always. So let me go back to the lab so that I have it queued up, okay, when I am ready for it. Okay, so let me create a REPL and let's just look at the look at decision making in Go. And first, I'm just going to show you a simple example of it. So let me make a variable here. So I will say a var x int equals 10. And then I'm going to do an if statement. So if, and now what I'm about to do is a Boolean expression. And after I write it, I will put it up in the note. A Boolean expression is simply code that you write that has a true or a false answer to it. So here's a Boolean expression. If x is exactly 10. So the Boolean expression here is x equals 10, and that's either true or it's false. This double equals, by the way, that is a test for equivalency in Go. Let's make some notes about that as well. Nope. Nope. So be very careful about this one specifically. If you want to check to see if one thing is equivalent in value to another thing, you have to use double equals. The single equals is assignment, and it is used to overwrite a variable. So we do not want to overwrite x here. We want to just check to see if its value is equivalent to 10. So the way Boolean, that's it. The way they work is it's either true or it's false. It's either true that x is equivalent to 10 or it is false that x is equivalent to 10. The way the if statement works is the block of the if statement. So notice that I put it in a block. The block of the if statement will execute if the Boolean expression is true. So if it is true that x is equivalent to 10, the things inside of the if statements blocks will execute. Let's just do a func.printf. X is equivalent to 10. And then we'll put printf, thanks for playing. Let's put an extra blank line in front of it. Okay, so this takes some practice to learn how to read these things and to understand what happens to the code around them. So when this program executes, func main is called automatically. We don't see it, but this is where the program starts running from. This variable is created and given a value of 10. And then this Boolean expression is evaluated, and it's either true or false. If it is true, then the contents of the if block are executed. If it's false, the contents of the if block are not executed. And then the program continues the next line after the block and does whatever follows. So no matter what, thanks for playing will execute, because there is no decision logic that would prevent it from executing. And we know in this case that x is in fact equivalent to 10. So this program will print x is equivalent to 10, and then it will also print thanks for playing, which is not dependent on any Boolean logic. All right, so x is in fact equivalent to 10, thanks for playing. Pardon me. If we make x be 9, that would cause this Boolean expression to evaluate to false. So 9 is not equivalent to 10. So the contents of this if block will not execute, and then the program will continue at the next line down and then still execute thanks for playing, which is not covered over by any Boolean logic. Thanks for playing, and that's the only thing. Okay, so there's one. That's the if statement. Let's do some comparisons before we move on to anything fancier. Greater than, less than, greater than or equal to, less than or equal to, not equivalent to. We'll start with those. So these are the ways that you do comparisons. Double equals to test to see if two things are equivalent. Greater than, as you might expect, to see if one thing is greater than another. Less than, one thing is less than another. Greater than or equal to. So these are all the same operations that you're familiar with. Some people will reverse the equal and the greater than in their code, which you can't do. You can't put the equals first, but just read it to yourself and speak it to yourself. So when we describe that comparison, we say greater than or equal to. So greater than first or equal to second. Less than first or equal to second. But those are the same comparisons that you are accustomed to. And then we have the exclamation point equal, which means not equivalent to. Oh, that's true. Yeah. So Rengo, or is it Rengoku? I forget. Anyway, in chat, Rengo noted that not equal to appears in the unit tests a lot. Yes, and that's exactly the place in the way that it's used. In fact, those are if statements, aren't they? So yes, if you like Rango has obviously done, if you go read the unit test, you will discover that I am doing this kind of logic, and I'm often looking to see if what the test expected is not equal to or equivalent to what the function produced as a result, then that is an error and it prints out an error. Nice catch, Rango. That's a good one. And that's exactly right. Not equivalent to. So we'll try several of those out and just kind of imagine what's going to happen. Most people don't struggle a whole lot with these comparisons, really, because you're familiar with them from a variety of math classes at this point, probably. All right, so let's leave x having the value 9 and write some tests and just ask ourselves what happens. So would it be true that x is less than 10? Yes, because x is 9, which is in fact less than 10. So that statement will execute. All right, we expected that. Is it true that x is less than or equal to 10? when it is 9? Yes. So if we run that, we expect to see, I should be changing this, right? I should have said less than or equal to on that one. Yes. Okay. Let's change this to 10 and ask the same question. Is x less than or equal to 10? The answer is yes. It's not less than 10, but it is equal to 10. So that does in fact work. Let's try just all of them. So is x greater than 10? The answer is no. X is exactly 10, which is not greater than 10, so it will not print as expected. Is x greater than or equal to 10? The answer is yes, because while it's not greater than 10, it is in fact equal to 10. So all these comparisons are the ones that you're familiar with. Less than or equal to 10. And then we'll do the not equal to 10, and this is false. X is equal to 10, so it's not equal to 10. So this is false, which means that this will not print. But if we change the value of x to be 9 instead, well, that is not equal to 10. So this one's a little funky, but you have to sort of just learn to read the Boolean expressions. Is it true that 9 is not equal to 10? Yes, it's true. 9 is, in fact, not equal to 10. That's true. So in that case, it does print because it's true that 9 is not equal to 10. So there's all the basic comparisons. We can get fancier with this, but we'll do that in just a moment. So that is the basic if statement. It is super, super useful. It is relatively easy to write. The comparisons, most of you will be familiar with sort of all the basic comparisons that we use. So all good there. So let's add now what we call an else part. And this one, for some reason, takes a while for people to get comfortable with. So notice how this is structured. We have an if part. So if it's true that x is not equal to 10, then we print the block that says x is not equal to 10. The else part is anything else. This is kind of, some of us would read this as otherwise. So if x is not equal to 10, do one thing, otherwise do something else. So this is another decision making where we can create a two-branch tree, two branches of possible outcome. X is not equal to 10, anything else. Notice, by the way, there's no Boolean expression on the else. It's literally anything else. Which in this case would be, well, if x is not equal to 10, then x is not equal to 10. Anything else is really x is 10, isn't it? So if we run this, x is not equal to 10. But if we make it 10, well, it's false now. 10 is not equal to 10. That's false. 10 is equal to 10. So the else part will execute. So x must be equal to 10. That was the only other possibility here. Let's do some others with this setup. So x is less than 10. So that's one possibility. If x is anything less than 10, then the if part happens. Anything else that x might be, x in this case would be greater than or equal to 10. So if it's not less than 10, then it must be true that x is greater than or equal to 10, which was the case here, because x is exactly 10. So if I say x is 9, then the if part happens. X is less than 10. And notice the else part didn't happen because the if branch matched. So one thing to note here is that with an if-else setup, you can only get one or the other outcome. You can't. There's no way to make both happen. You're either going to get this one, else you're going to get this one, and the two can't cross in any way. You're going to get the if part, or you're going to get the else part. Now, some people want to do this: x greater than or equal to 10, which logically is correct, but Go won't let you do that. Syntax error on line 22, else must be followed by some other stuff. So you don't use an else when you want to set up a condition. You use an else when every other condition should get the same result. Less than 10 or everything else. So there is no Boolean expression on an else. A lot of you are going to write Boolean expression on else's. So I'll try to plant the seed in your head, and I just know this from many years of experience that a lot of us want to write a Boolean expression on the else. You can't. You'll get an error. In every language, by the way, you will get an error if you put a Boolean expression on an else. It's everything else. And everything else doesn't need any description or Boolean expression. It's everything else that's not the if thing. So everything else that's not x less than 10 is x greater than or equal to 10. Everything else that's not x equal to 10 is x not being equal to 10, as an example, right? Which should trigger in this case. So that's the if-else statement. Learning when and why to use like when would I use an if statement by itself versus when would I use an if-else statement takes practice on a variety of different problems. So this is another one of those things like functions that we will practice, and you will find pretty quickly that you can't write any kind of realistic program unless you have decision-making capabilities. So we want these, and it's well worth practicing them. So when would I use an if-else statement? If you are looking at a situation in code and you can say to yourself, well, if this condition exists, I'm going to do this special thing. Otherwise, I'm going to do something completely different. That sounds like an if-else statement to me. All right, let's try something else. Now let's turn this into something even bigger. So I'm going to erase this. Well, what I'm going to do is comment it, and I'm going to get it out of the way. Let me shift-tab these back. Okay. So now let's do a more elaborate decision tree. So sometimes you have a decision to make with more than 2 branches. So let's do one. Let's change this to be a float 64. Let's call it a temperature. Make it a float 64, and we will set the temperature to something like 99.5 degrees. And now let's write a decision tree that prints out a different message based on the temperature. So let's say, for example, if this temperature is less than 32.0, we'll do it in degrees Celsius. So if our temperature is less than 32 degrees, let's say if it is, we should say less than or equal to, because 32 is freezing outside. All right, but we have a variety of different conditions, right? So if it's not less than or equal to 32 degrees, perhaps, else, if perhaps, so we need another condition here. If the temperature is less than or equal to, let's say, 60 degrees, then we will say it is cold outside. So now we're setting up for a decision tree that has multiple branches, but only one branch will actually match and be taken. So if the temperature is less than 32 degrees, we'll say it's freezing. If it's not less than 32 degrees, then we'll check to see if it's less than 6 degrees, in which case we will say it's cold outside. If it's not less than or equal to 60 degrees, let's see if it is less than or equal to, let's say, 80 degrees. In which case, I will say it is cool but comfortable outside. So hopefully you can see this tree getting its branches. So, but the way this will execute is that Go will go to each branch and attempt it. So Go will first check the temperature against 32. If it finds that that is not true, it's going to go test the next branch and then test the next branch. And it's going to keep testing branches until it finds a match, at which point it goes down that branch, and that's the end. All right, so thank you. Okay, so temperature less than 32. If it's not less than 32, then maybe it's less than or equal to 60, then it's cold. If it's not less than or equal to 60, maybe it's less than or equal to 80, in which case I would call it cool but comfortable. If it is, let's say, less than or equal to about 94 for me, I don't know. We'll say it is warm outside. And then we will attach a final anything else. So if it wasn't less than 32 degrees, and also then it'll check 60, but it wasn't that. It'll check 80, it wasn't that. It'll check 94, it wasn't that. So anything else means that it is 94.1 or higher, basically. We'll say it is hot outside. So there is a single decision tree with multiple branches on it, all based on what the temperature is. And the way Go will evaluate this is it's going to work its way down and test every possible branch until it finds a match. So this 99.5, that's not less than 32. So it's going to check less than or equal to 60. Nope. So it will check less than or equal to 80. Nope. So it'll check less than or equal to 94. Nope. And then, well, that falls into the, well, anything else is just plain old hot. So let's try it. All right, so it's hot because it's 99.5. So let's try some of the others. Let's try, well, we'll just work our way backwards. So let's try 90 degrees. And we'll just guess in advance. So 90 is not less than or equal to 32. So Go goes to this next branch. Is it less than or equal to 60? It is not. Is it less than or equal to 80? It is not. Is it less than or equal to 94.0? It is. So Go chooses that branch, and then that's the end of it. Nice one. Yeah, so Kevin worked this one out. It's going to say it's warm at 90 degrees. Good one, man. It's warm. All right, so now that I've got a couple of you talking, I will, I'm going to mix it in just a little bit. So I'll give chat a moment and see if someone knows where 32.1, which branch that finds. Nice one, Kevin K. It is cold outside. So 32.1 is definitely not less than or equal to 32. So it's going to test less than or equal to 60. Yes, it's cold outside. And notice none of the other branches happen because only one of the branches can happen. It's cold outside. So a nice one. Let's do a... Oh, sorry, that was uncool of me. Well, anyway, it'll take more typing. So which branch does 60.1 degrees get us in? Cool but comfortable. Nice one. Kevin K is all over the right answers for this one. 60.1 is not less than or equal to 32. It is not less than or equal to 60. It is less than or equal to 80, so it will be cool but comfortable outside. Pretty cool stuff. Let's make it be freezing. I can't imagine. Oh, we'll make it 20.5 degrees. So that's freezing, of course. And I just want you guys to notice that only one branch. This is one tree. If, else if, else if, else if, else. There's only one tree. And you only get one branch of one tree. All right, now I'm going to do something a little tricky here. It turns out that you are not required to have an else part if you don't want one. So if I take the else part out, I'll restore it in a moment. So I'm going to set this temperature. And then ask it's not a trick question, but it might feel tricky to come up with the answer here. So I'll kind of just say it's kind of a trick question. Which of the branches of this tree will execute? Nice one. So Kevin K is really owning this decision-making stuff. That's correct. Nothing happens. There is no branch that picks up 94.3. I took the else part off, which means there's not a everything else branch anymore. And the logic of the current tree doesn't account for 94.3, so nothing happens. So that's absolutely correct. And it's true. Wait, what? I'll just paste it back in. So the else part is not required ever, but you need to consider whether or not you are missing part of your outcome to not include an else part. So just be careful about that kind of thing. Okay, so there's another. Let's switch these out for something else. So let me shift tab these. I'm just getting these out of the way real quick. Shift tab, comment out. Oops, forgot this thing. Okay, so let's go back to a very bare program. So let's now do this instead. Let's make a var and we will call it a letter and make it be a string, and we will set it to be the letter A, let's say. So you've seen an if statement, you've seen if else, you've seen if else if else. So now let's add the last thing, which is the switch statement for decision making, and then we'll start looking at ways to do more elaborate decision making after that. So I switched to using a string now because you can do comparisons on strings. They can be trickier. Doing comparisons on integers and floats is way more certain than doing comparisons on strings. And I will just give you, I'll give you a straightforward just how do you set it up, and then I'll show you why strings can be tricky. So in fact, let's do fruit, and we will say apple. So the last kind of construct is the switch statement. And it is set up very, very differently from the if-else, even though it means the same thing. So the way the switch statement works is you say, I'm going to switch or branch. I wish it were called branch. Branch on fruit, but the way it's always been done is we switch on the value of fruit, and it also has a block. So the switch simply means that we are going to define branches based on the value of fruit. Switch branches, depending on what fruit is. And the way you write these is you say, in the case that fruit is apple, I will print I like apple. So some people like these. They find them very comfortable and natural. I personally do not. I can use them, and I do occasionally use them when they seem like a good fit to me. But I'm not a huge fan of the switch statement, just so you know. If you decide you are, that's great. There's nothing wrong with it. If you decide that you are not comfortable, like I'm not comfortable with them, that's okay as well. But anyway, you define your branches with case statements. So the way I read this is, in the case that the fruit is apple, then I will print I like apples. In the case that the fruit is orange, I will say citrus is healthy. I don't know. In the case that it is kiwi, no offense, you guys, not a fan. Because it has hair on it, and also it's just kind of like solid sugar on the inside. And then how do we do the else part? How do we do the everything else in a switch statement we do with default? In this case, I'm actually going to be cute and print out the fruit. I have never tried whatever that thing is. So this is what a switch statement looks like. They're weird looking. Some of us find them awkward, some of us don't. So we're switching on the value of fruit, and then our cases define what happens for different values of fruit. These are the branches, and only one branch will take. So if I run it right now, since the string is apple, it's going to match this first one. It's going to do this first branch, and that will be the end. So I like apples. That's pretty obvious, right? Let's do banana. So if I make the fruit be banana, well, it won't be apple, it won't be orange, it won't be kiwi, so it's going to land in the anything else that didn't match the defined cases. So it will say I've never tried banana, even though that's not true. So there is I have never tried banana. By the way, you don't have to have a default, just like you don't have to have an else part. You don't necessarily, you can just ignore things if you want to. So in this case, nothing happens because I took the default out. Okay, so now let's look at why strings can be tricky. So let's put apple back, but I'm going to capitalize it this time. And it, oh yeah, it falls into here. I've never tried apple. Wait a second, what's going on? Well, comparing strings is case sensitive in most programming languages. So apple spelled with a capital A does not match apple spelled with a lowercase a. In Go, you can actually, there are better ways to do it than this, but one of the things that you can do is you can say, in the case that apple is spelled with a little a or with a big A, then I will say I like apples, and it will work. So you have the ability to kind of stack up variations to handle this branch. Of course, that doesn't do anything for the all caps apple, which still doesn't match. Right? I've never tried apple. Well, that's not true, but it was all caps. So we will see, we will work on an algorithm in this semester where we deal with this lowercase uppercase problem. Nice. Yeah. So Kevin K asked, can you lowercase uppercase? And you can. So I'll just say it, but I'm not going to do it because I'm afraid it might make people start to feel a little overwhelmed, but there is a strings package in the Go language. So if you do Go package strings as a Google search, you will find one of those documentation pages, and you will find in there a function, strings dot probably to upper and strings dot to lower, that will all upper or all lower a string for you. So yes, you definitely can do that with the strings package. But I didn't put it in code because I didn't want to scare anybody away. Okay, so Switch does have this sort of extra little bonus feature inside of it. You can also, by the way, it's another thing that I don't find myself doing, but just so you know, you have this option. You can use a switch like this as well. So let's make a, we'll have a, let's put a number in there, make it an integer and just say 50. So we can switch on numbers too. And we can do things like this. We can say case number less than 10, small number, case number less than 50, medium number, kind of a Goldilocks thing, case number less than 90, large number, case number greater than or equal to 90, or I could just say default. Everything else, I'll just say, well, anything greater than or equal to 90 is a huge number, let's say. So you can also do this with the switch, where you can kind of do the comparisons inside the switch to make your branches. It's not a thing I use, except for no, I didn't as type int. Yeah, that don't work. Why am I doing that? Oh, I'm glad I showed you. I think maybe I saw this in one of your readings, and maybe they were saying you can't do this. So I'm going to say you can't do this unless I did something wrong, but no. I'm going to say you can't do this. So in a situation like this, this is better done as an if statement. Else if, wish it wouldn't do that part. Else if, I don't know, maybe someone will report back to me about what it was I saw that I thought, that's weird. I don't know what that is, but I thought I'd try it. All right, so let's switch this back to an else because the ranges don't match. And maybe that's what the reading was trying to tell you. So the way I use switches, which I don't very often anyway, is for exact matches. Whereas if I'm comparing kind of ranges, then I'm going to use if, else, okay, so, oh, hold on, my REPL is busted. Okay, there it goes. All right, so now let's start doing some fancier things. And I'm going to make a function now for this so that you get used to seeing functions with these decisions in them. So let's make a function. I'll call it enter private club. And we will make it dependent on what? We'll make it dependent on a password and a secret number also. So I want to show you a slightly different, fancier decision making, which will be dependent on two different things. So we'll start just by, in fact, let's, we'll just print out things. So in this case, we have this function enter private club, and I'll capitalize it. If the person has the right password and a secret number on top of that, we will let them in the private club. So that would look like this. If the password is okra. It's a word I like to play with in these situations. And, so the double ampersand is called logical and it allows you to combine two Boolean expressions into one whole thing. This will make sense to most people just kind of out of the box. So to get into the private club, you need the password to match and you need the secret number to match. To get in. So this is logical and what it means is both sides must be true at the same time. So it must be true that the password is okra and it also must be true that the secret number is 42. So notice I don't have an else part here. So if you don't have both of those things, then nothing happens. Let's try it for main. Enter private club. So first I will try a successful one. So I'm going to give it the right password and the correct. But then let's try some options. So enter private club where I have the password, but I don't have the secret number. I will try to enter with the wrong password and the right secret number. And then I will also try to enter where I don't know either of those things. So what should happen is the first one should let me in because the password and the secret number have to match. The second one should not let me in because while I have the password, I don't have the secret number. So the password is true, but the secret number is false, and they both have to be true. In the third one, I have the right secret number, but I don't have the right password. So the password is false, and they both have to be true. And then in the last one, they're both false, which means that I'm not getting in. So I should only get in on the first one. So I got in on the first one. I guess we could have done extra outputs to be sure of that. But anyway, that's the first one where they both have to match. Now let's make a change. So I can also instead, these are the pipe character, the vertical bars, which are over the enter key. This is logical OR. And what logical OR does is it checks to see if either one or the other is true. So if you have the password or the secret number, you'll get in. And that should allow us in on the first one because they're both true. On the second one because I have the password and it is either one or the other can be true. The third one I get in because I have the secret number because it only has to be one or the other. And then finally the last one I won't get in because neither of them is true. So I'll get in 3 times here. I think that's all the basics for constructing logic. Yeah. So let me move some things out of the way. Just go up here to the top and I'll make a new program sort of above the top of all of that. So that's all the basics. Takes practice. You'll have readings to back all this up. Experiment with switches, experiment with if else. I just rarely use the switch statement myself because it just looks and feels weird to type to me, so I don't use it very much. But that does not make it wrong to use it. If you like it, then use it like crazy. If you can make your logic work, then you make your logic work however you can make your logic work. Okay, I'm going to switch over to the lab and then do a little example around it in the hopes of explaining to you what the lab is talking about. So first thing is let's just look at what the lab is, and then I'll develop some examples in the hopes of explaining to you the meaning of some of these terms. So in the lab, you're going to see the term encode. And all I mean by encode is check for a particular value of a string and return an integer in place of the string. We encode things all the time. At Butte College, as an example, we have a database that has all of our names in it, mine included. And if you feed your name into that system, you can get your student ID, which is a form of encoding you in the system. So your name is encoded to your student ID number. And then we can also go the other way around. We can put your student ID number into the system and decode that, as it were, to get your name back out. That's all I'm talking about here. Is when I say encode and decode, there's nothing fancy about it. It just means, in the case of this function, if apples comes in, you get code 1. Why code 1? Because I made it up. I'm going to make up an example here just so you can see what I'm talking about a little bit. Decode is the same thing, just in reverse, right? So if you give me the number 1, I'm going to give you apples back. Just going to do it in reverse. Why apples and 1? Because I made it up, which is usually the case with encoding and decoding things. Someone had to make up the code. We have a system that probably automatically assigns just by counting up an ID number each new student who enrolls. So that sounds way, way, way fancier than what it actually is. But let's do an example in here, just in case you're feeling bad about that. I'm going to show you where I'm getting this from, by the way. So I was just looking for something that I could use, some kind of subject matter that I could do encoding and decoding on. So I'm using this kind of Dungeons and Dragons kinds of stuff. There's like 20 animals in here. So I'm going to go fast, but I'm going to write an encoding and decoding system for at least some subset of these creatures in this list. So what would that look like? Well, I'm going to make a function. I'm going to call it Encode Creature. I'll be using the creature's name, which will be a string, and I will be returning an integer, which will be the code that I am going to assign to each creature. I'm going to make the codes up. And in fact, probably I'll just use the same numbers here. So dragons will be code 1, wizards will be code 2. So here we go. So if creature name equals dragon, I'm going to do singular because that's what I want. And then for this encoding, it simply means send back a number. So I'm just going to literally send back 1. So if this branch matches, if dragon comes in, then code 1's coming out. I'll prove that. So I'm going to make a var creature code, which will be an integer, and then I will say creature code equals encode creature dragon. Let's make an else part in here just in case. Let's return code 0 for any creature that's not matching. And then I'll just print it out. So format.printf dragon code creature code. And then let's try a non-existent one too. So we'll reuse creature code and we will attempt to encode, for now, a wizard, which I don't have any encoding for right now. So that should come back as a 0. Wizard code. So here I am encoding dragon, just getting a number for it, and trying to encode wizard, which I don't have. Oops, return 0. So anything that's not a dragon is going to get a code 0 for now. I'm going to go ahead and copy this a few times and then add some codes. So 1, 2, 3, 4, 5. Let's go back to my creature list. Hobbits 6, elves 7. Okay. So we'll do a hobbit. Elf. I know not everyone's into elf code. What else? One more off my little list. All right, goblin. I like the word goblin. So for now, I don't have any encoding for any creature other than dragon. So all of the codes are going to come back 0 except for dragon, which should be a code 1. So dragon's a code 1 and all of the other codes are code 0. So now let's add some encoding for other possibilities. So let's push the else down. Else if creature name equals wizard. I will return, what code was that? That's a code 2 on that page, which is not really a code, it's just a numbered list, but I have decided to use that as my code. Else if creature name equals hobbit, elf, goblin. So hobbits next. Hobbits were, that's code 6. I'm just using the number off this list as the code for my made-up encoding system. Else if creature name equals elf. That was a code 7. And finally, I have equals, what was it? A goblin, which on this page is a 18. And then I will bring this thing up to make the tree look proper. So there is a proper decision tree that encodes, basically returns a number associated with a particular creature in this system. The numbers are all over the place. That's fine. They're just made up codes to go with each creature that I drew from that list. And if I try to encode anything that's not on my list, like a human as an example, I should get a 0 back. Just a regular human. So let's see the codes. There we go. Yeah, so human is the only one that's a 0. All right, so hopefully everyone gets that. That is very close, and I will put this link on the lecture page. Let's decode creatures now. So to decode a creature, we simply take the creature code, the number part, and we send back the string, which is the name of the creature itself. So in reverse, if the creature code is 1, let's do it as a switch just for the heck of it. Switch on that creature code. In the case that the creature code is 1, that is, scroll up so I can see it, that's a dragon. In the case that the creature code is a 2, that would be a wizard. So notice I'm using the same codes, just in reverse, right? So I'm decoding. In the case that the code is 6, that's a hobbit. In the case, I remember this one now, I just read it, that's an elf. And in the case that it is 18, that is a goblin. And then I'll go ahead and have a default. So for anything else, I'm just going to say error. Don't know, can't help you. That's just flat out an error. Okay, so let's try some of those. I'm going to do this in a slightly more compressed way. So F code 1 is S, and then I'll just call Decode Creature here and pass it the value 1, and that way I can go a lot faster. 2, 6, 7, 18. And then I'll try some other random code like -1. There's 2, 6 is a known code, a 7 is a known code, and an 18. And then I'll pass it, oops, 2, 6, 7, 18, -1, and see what the decoding looks like. So here's the decoding. Code 1 is a dragon, that's true. Code 2 is a wizard. Code 6 is a hobbit. Code 7 is an elf. 18 is a goblin. And -1 is an error. That is not a valid code. So that's what the lab is talking about when it comes to decoding and encoding and decoding. You're going to do something very, very similar. How am I on time? I'm doing okay on time. All right, so that's encode decode. Shipping charge is a simple if else, so I'm going to leave that one to you. It's very short. Take walk. I'll do a quick well, I did kind of just do a quick example of that. But anyway, take walk sounds very scary and fancy. It implements an ID3 decision tree. All that really means is that it's a decision tree that may use some combination of, in this case, 3 different conditions. So I'm going to speak this to you and then leave you to work on it. Well, no, maybe I'll do something similar in my example. So let's do something similar. So outlook humidity. So let's say, let's do a similar kind of tree. So we will say, use magic. So let's have a use magic where we are given a, well, what would you have to know? So let's say that we have a creature name. Let me see what these are using. They're using all strings. Okay, so we'll do something similar, but not exactly the same. We'll take this creature's name. We will take let's say a level just for fun, which will be an integer. And then what else do we want to decide if we will let them use magic? Their name, their level, and let's also say their, how much mana do they have? Since creature level and creature mana, by the way, are both integers, we can group those up. And that will return true, they can use magic, or false, they can't. So this is a very similar kind of, similar to ID3 decision tree in lab. So let's see, what would we allow to use the creature for magic? So let's say if they are a wizard and they have a bunch of mana, then yes, they can use magic. Let's say another condition, though, would be that if they have a high level and adequate mana, then yes, they can use magic. And we could keep going from here, right? So we could say, well, maybe the level isn't, or maybe if the level gets sufficiently high, then they don't need as much mana. No, that wouldn't trigger though, because 20 would trigger greater than or equal to, oh yeah, so then yes, you can use magic, and then in every other case, you cannot use magic. So this is similar to that tree where we're using a combination of the different available pieces of information to decide if we're going to let the creature use mana. So that's similar to the ID3 decision tree that is in the lab here. So if the outlook equals sunny and the humidity equals high, return false. If the outlook equals sunny and the humidity equals normal, then return true. So hopefully that's enough for you guys to work with it. And here's the else part. Anything else is just return false. So yeah, hopefully that is enough to get you guys into that problem. They're all strings. So you're looking for outlook equals sunny and humidity equals high. Else if outlook equals sunny, that's a return false. Outlook sunny, humidity normal, return true. Outlook overcast, return true. Outlook rainy and wind equals strong, return false. Outlook rainy and wind equals weak, return true. Else, return false. That's what that one is. But I want to get to this one because this one probably scares people. Might scare people the most. So this one is also kind of an encoding function where we pass the function a card value, which will be in integers. So a card value of 1 is an ace. Card values of 2 through 10 are just what they are. A card value of 11, 12. So I'm going to actually probably, I think, start this partially in my sample to help you with it in the interest of not burning up too much of your evening. So let's see how this is going to play out. Okay, so we get a card value and we get a suit, which will either be big C or little c for clubs, big D or little d, and so on. So a string representation. So this is the part that might be new to some people. Here we go. Anything that's not between 1 and 13 just becomes an error. And then the suits are spelled out that way. And then there's some examples of what's expected based on some given arguments. So let's do some. So let's start by giving ourselves a string to represent the card. And then once we have figured out what that string should be, we will return it. So this is empty, and we are about to populate it with the proper information. So what is of interest to us? If the value is 1, then the card is an ace. And we should section this off. So deal with the face value. And then separately, we will deal with the suit. So if the value is 1, then the card is an ace. And then separately, we can say if the suit is a little c or the suit is a big C. This is logical or, which means if either of these is the case, if it's a little c or it's a big C, that's clubs. So the way we do this is we need to add the suit onto the card that has already the word ace on it. So the way we do that is we will say adjust the card by adding clubs to it. So we'll take whatever the card had for its face value, and we will add onto the back of that the word clubs. So right now, a 1C, little c or big C, should say ace of clubs. Let's try it out. Let me get rid of all this creature code stuff, at least comment it. All right, let's try it out. And we'll just try it out directly in, so let's just say, here's the card, whatever it is, and then we will do, what does it say? Pretty playing card. Pretty playing card. And it should be the case that a 1 and a little c should say ace of clubs. Let's try it out. Creature man, what? Huh? What line? 46. Creature man. Oh, creature mana. That's not even involved in the code right now. Okay, ace clubs. Close. So we have the ace part right, and we joined on to the back of it the clubs part right, but we're supposed to have an of in between. So let's, in between, let's insert of. So we'll take the card after it's got its face value, and we will add on to that the of. Close. Ace of clubs. All smushed together, but it's supposed to have spaces in there. So when we put the of in, let's put the spaces in with it. Ace of clubs. Let's try it with the big C and see if we get ace of clubs again. Should be true that either little c or big C, they're both aces of clubs. So pretty good so far. Let's add a couple just so you can see adding a couple. Let's do a 2. It should just say a 2, right? Yep. So let's try a 2 of clubs. 2 of clubs, which is what it's supposed to do. That one's 2 of diamonds. Also if suit equals little d or suit equals big D, we will add to the end diamonds. And then let's change this one to be diamonds and see if we get a 2 of diamonds. Okay, that's good. I'm just kind of using these examples as my guide. Okay, so it also says anything that is invalid should return error of errors. So what would that look like? Well, for now, let's just say anything else, which would not be correct, of course, but what I'm told is that any unrecognized value should say error of, and then down here also any unrecognized suit should say error of error. Yeah. So the suit will be replaced by error. The of will still go in there, and then the card, the face will be error. So let's try an error one. We'll just do the same as the example, which is a 0 of x should be an error of, oh, here's where I made the mistake. I just made the whole card say error instead of attaching that word error to the back of error. So I got to be careful about that. 2 of diamonds, error of error. So we will need to insert more, right? So I will need to insert more stuff. The value is 3. Then I will say card equals 3. Bring that back up so that it looks pretty. Anyway, hopefully that's enough to give you the idea. Let's try one though. Let's try a 3 of diamonds. And a capital D should work just as good as a little d. So there's my 3 of diamonds. Okay, so I hope that's enough. And it is embedded here in my sample REPL. So the link will be on the lecture page. Hopefully that's enough to get you guys through the lab. I did leave you the challenge of working out what sounds scary because it's an ID3 decision tree, but it's just an if, else if with some ands, logical ands in the mix. Whereas Pretty Playing Card is a couple of if, else if type statements with a few logical ors in the mix. Okay. Hopefully that's enough for those things. And then let's close out by looking at the project. All right, so the project is basically one program that plays 2 mini games. And I'm actually going to get us a setup, but I'm only going to do it here on the stream. I'm not going to post the code yet, and I may never. So anyway, stream exclusive. I'm going to set up a starting point for this thing, and then consider how this would work. So we're going to do a number guessing game, and I can tell you that requires looping, which we get next week. So by next week, we will have all the tools needed to do the number guesser. Rock, paper, scissors does not require looping. Pardon me. So we actually have the ability to do this. So I'm going to give you a hint to get us started in my last few minutes. So let me get the link to this. This goes up with samples. And then let me make a new REPL. Private. Go 20. Project 1. Project 2, rather. Okay. So I'm actually going to show you a fair amount of the setup here because I have just about 10 minutes to do this in. But I'm not going to post the code. So please get the word out to people that if they want this kind of assistance on the project, it's in the live stream. And this is just there to sort of give you the idea. So we are making a game. We're making a program that lets us choose to play 2 different games. The way I do this, I still have my sort of main let's play a game. I'm going to change this to a printf, and I'm going to put a couple of new lines after. Let's play a game. So we have a situation where we want to let the user pick between the number guesser and the rock, paper, scissors game. And the way I typically do that is I give them a menu of their options that looks something like this. I like numbered menus. So I would probably say, like pick number 1, play number guesser, new line. Option number 2, play rock, paper, scissors, new line. And then you need to have typically, like what if they change their mind? I usually make it the 0 option, which you'll find in time makes some other aspects of our programming life easier. So I ask the user to type 0, which would be to exit the program. So this is how I would manage the problem on this project of getting the user to select which thing they want to play and getting them there. And then I have a little prompt. So your answer goes here. Some of you use this style of prompt already, so I'm kind of stealing it from you because I think it looks kind of smart. So we have a menu for the project. And then you're going to see some familiar things. These are all familiar. It's just printing stuff on the screen. There's actually a couple of you who have already been doing menuing systems like this. So what you do then, you present the options to the user, and then you, this last one serves as the type something in now spot. If it'll, there it goes. So type something here, and since you've asked them to type something, well, let's get their choice. And then what we do is we use our newly acquired decision-making skills so to check their choice. So if they choose 1, they're going to play the number guesser. Else if they choose number 2, F, get ready. Otherwise, the only other option that we offered them was to exit the program. So let's just say, come back soon. So we don't have the games themselves set up, but we do have a little menuing system now. We do have the ability to prompt them for, read in their choice, and then we use our decision-making abilities to go down the proper branch. Either to play number guesser, which we have not coded yet, but we'll get set up for that maybe next week. So if I run this, I now see my menu. It's waiting for me to make my choice. So I'm going to say, okay, I want to play number guesser. So right now the program is just going to say, hey, I got you to the right branch. This is the number guesser branch. If I type number 2, the program is going to say, I got you to the rock, paper, scissors branch. Program option number 3, which is exit, should get me down the please come back soon branch. So now I have my menuing system and I'm getting ready to go. I have 3 minutes. Let's go ahead and take the next step. So what does it look like to go down? Let's do the rock, paper, scissors branch. Well, what it looks like is we're going to make a function. Rock, paper, scissors. And not a fancy function with parameters and return type, but simply rock, paper, scissors. For now, we may want improvements later, but let's just start with this much. And instead of saying rock, paper, scissors, get ready here, let's move that to the function. And then when we go down the rock, paper, scissors branch in main, instead of printing something out, we will call the function, which will take us here, which should show us the output. So let's pick rock, paper, scissors. It got us there. 2 minutes. So I can do just a couple more things. So what does it mean to play rock, paper, scissors? The computer is going to play a random selection. Oh, wait, random. Well, I know that random requires math rand, and it also requires time for the purposes of seeding. So I'm about to use the random number stuff that I have already practiced in last week's lab. All right, so we need a random number here. Well, if we're going to use a random number, the first thing we're going to do is we're going to go right to the top of main, and we are going to say rand.seed time.now.unix nano, which I just have memorized at this moment, although I will forget it when I stop using it soon. That's required because I'm going to be using random numbers in my program, and I'm only going to do it this once. All right, so I've seeded because I know this is happening. Okay, so we need to get the computer play and we're going to use a random number and in a certain range. So there's only 3 options here. So I want the random number to only go, in this case, would be 0, 1, or 2. That's fine. I just need the computer to have the possibility of playing one of 3 possible outcomes. So I generate a random number that if I put 3 in here, I get 0, 1, or 2. This is one of the reasons why I'm having you do encoding this week, is because this is an encoding. I have to decide what 0 means, what 1 means, and what 2 means. And what that looks like in the program is I will say, well, if the computer play is equivalent to a 0, then I will simply decide that that is going to be computer plays rock. Another possibility is that I get a code 1. So this is like a random encoding. The only codes I can get are 0, 1, or 2 off this 3. Kind of like the dice rolling thing. If you wanted to, by the way, you could add 1 and then make it be 1, 2, or 3. So hopefully you're seeing why we've been doing some of the activities we've been doing. All right, so let's change that. The code 1 will be a rock. Code 2 will be paper. There's only one other possibility, which is a code 3, so I don't really need the logic for that. I will just say, well, if it wasn't 1 and it wasn't 2, then it had to be 3, which is scissors in my encoding scheme. So let's just try it, and the computer will make its one guess, and then the program will end in what? What did I do wrong? What is that supposed to look like, people? I don't remember. Time. Is it capital T time? Oh, no. Right. So, oh, I know what it is. It's this N, isn't it? Time.now with a capital N. Thank you. Yeah, someone in chat noticed that my N was wrong. All right, so let's play rock, paper, scissors. And this time computer played rock. If we run it again, in theory, played rock again. All right, they played scissors that time. So that's a good start. That is live stream only stuff. So I'm going to spend 2 minutes just kind of showing these on the screen. I will be back in here next week to help you kind of move this along a little bit further. But for now, here's what I've done in my starter for Project 1. I have these imports, which include math, rand, and time, because we're going to be using random numbers for both the number guesser and the rock, paper, scissors game. Also on the screen is the starting point for the rock, paper, scissors game. All I'm doing now is printing a message saying you're in the rock, paper, scissors game, and then I am generating a random computer play and printing a message that tells the player what the computer plays. Of course, before you do that, get the player's selection before showing them what the computer plays. All right, so that's better, right? We don't want them to see what the computer plays before we have asked them to make their own selection. And then somewhere at the end, we will use decision making to determine the winner. So there's the rock, paper, scissors start. And then finally in main, that's all of main right there, I think. Yep. we have a menu. So we seed the random number generator because we're going to be using it in 2 places. We have a welcome message. We have a menu. We let the user select from the menu, and then we use our decision-making powers to take them down a branch that matches their choice from the menu. Play the number guesser, play rock, paper, scissors, or come back soon. So for now, that is stream-only stuff. I will be looking at this exact same stuff and building it out a little bit further next week to help you guys. But otherwise, it's 5:35. I should stop. Thank you a lot for sticking it out. If you are here for the live stream or if you're watching the lecture on video later. Thanks for your input in chat. I very much appreciate it. So have a great week. I hope that you have seen everything that you need to do the lab and hopefully also to get started on your project. And I will see you next week. So take care.